Welcome to Group 4's Concrete Mix Design. I'm going to walk you through our project starting with the background and objective of our design. As a class, we decided designing the strongest concrete would be the most exhilarating and interesting thing we could do. Thus, we did just that. Strong concrete, classified as having the capacity to withhold around 6,000 psi, is used in the real world for projects such as high-rise buildings, bridges, or really anything that weighs a lot and needs supported by concrete. But what makes concrete strong? That was the question driving our research into what materials, additives, or water to cement ratio would result in the concrete with the highest compressive strength. So after scouring the internet, articles, and journals on the topic, we found that the materials and additives that led to a high strength product include number 57 limestone with a density of 1,566 pounds per cubic yard, number 8 pea gravel with a density of 847 pounds per cubic yard, concrete sand with a density of 355 pounds per cubic yard, steel microfibers with a density of 1.87 pounds per cubic yard, Class F fly ash with a density of 133 pounds per cubic yard, super plasticizer, and of course Portland cement with a density of 397 pounds per cubic yard. We found in our research that by using large amounts of coarse aggregate and steel microfibers, we could produce the highest compressive strength. Additionally, we decreased the amount of water we added to produce a water to cement ratio of 0.35. By decreasing the water to cement ratio, we decreased the workability of the mix. Thus, we incorporated the use of the super plasticizer, whose sole purpose was to increase the flowability of our mix. By using fine aggregates, we aimed to fill the small spaces between the coarse aggregates, therefore creating a high density mix which would result in a strong concrete. This chart shows how the coarse aggregates, number 57 limestone and number 8 pea gravel, have the highest density, thus proving why we tried to optimize their use. After determining the appropriate batch weight of each component of our mix, the fun could begin as we brought our design to life. First the coarse aggregates, then the fine aggregates. Followed by steel microfibers and water. And lastly, the super plasticizer. Our mix was noticeably dry and lacking enough cementitious material, but we decided to go through with it and see the result. Not to mention we were the only group to create a successful mix on our first attempt. Now came the testing. First we used ASTM test C143, the slump test, in which we determined the slump of our mix. Our mix slump was found to be 7.5 inches. Next came ASTM tests C231 and C138, pressure method air content test and unit weight. By using a measuring bowl of known mass and volume, we used a pressure gauge to measure our concrete's air content via water insertion into the bowl. First, we filled the container with the appropriate method of levels and rotting. Then we clasped the lid on to insert water and read the pressure gauge. Our air content was found to be 2.9%. And since we knew the mass and volume of the container, we found our mix density to be 134.7 pound per cubic feet. The last test for our concrete mix was to fill 3 cylinders using ASTM test C31. After filling the 3 cylinders, they were left to set and later cure for 7 days before performing our compression test. Before testing, the cylinders had noticeable segregation and large pore spaces within the cylinder, thus making it prone to failure. As noted before, more cementitious material and equivalent water could have aided in preventing this. To test the concrete strength, compression test ASTM C39 was used. Cylinder 1 was found to have a density of 145.382 pounds per cubic feet and a strength of 3,476 psi. Cylinder 2 was found to have a density of 143.113 pounds per cubic feet and a strength of 3,036 psi. Cylinder 3 was found to have a density of 146.356 pounds per cubic feet and a strength of 4,674 psi. As seen here, the density directly relates to concrete strength. Thus, by filling the pore spaces of our cylinders and creating more uniform concrete, our strength would increase and potentially hit that 6,000 psi threshold. We meant well with the use of coarse aggregate, but by overdoing it, we left our concrete prone to fracture. Areas where other groups edged us out was by using less large aggregate, having a more workable mix with a slightly higher water-cement ratio and a little more plasticizer, and by having 2 attempts at their mix. If given another go at designing a high-strength concrete, we would slightly increase cementitious material, slightly decrease our coarse aggregate contents, and aim for a mix that won't segregate, resulting in pore spaces in weak concrete. 4,674 psi concrete on our first attempt isn't too shabby, but we can only imagine the possibilities if given a second trial. We hope you enjoyed this video, and thanks for watching.